Okay, hi everybody. Today we're talking about real gases, and in the last video lecture I showed you this slide. It's some PV data, pressure volume data for carbon dioxide gas, and we're plotting pressure versus 1 over volume. We plot it in this way because we can make a simple prediction from the ideal gas law. Let me see if I can get everything set up here. All right, so this works. Good. If I rewrite the ideal gas law, I can write it in that form. P equals RT times 1 over Vm. And essentially that's predicting that I should get a straight line that goes through 0. What we can see from this plot is down here, molecules behave ideally, right? Straight line that goes through 0. But in this region, we see non-ideal behavior.
Non-ideal.
You predict the pressure would be someplace up here. In fact, the real gas behavior is lower than that. And so the question is why? That's kind of the question I left you with last time. And the answer is that the assumptions in the ideal gas model aren't perfect. Recall that the ideal gas model assumed that gases effectively took up no space. The molecules themselves took up no space, and that there were no interactions between molecules except for collisions. Well, we're chemists, and we know that that's actually a really sort of bad model. If atoms and molecules took up no space, and if atoms and molecules were not allowed to interact, chemistry would be an incredibly boring subject. Excuse me. Maybe you couldn't see it, but that was right into the elbow. It's a good cough. So molecules interact, right? And that's what causes this type of behavior. This is what we call real gas behavior. I think the easiest way to understand it is with a kind of plot like this. So you've seen this before in a general chemistry class. It's a plot of the potential energy as two nuclei approach one another. We use this to explain a chemical bond. Molecules are infinitely far apart, someplace out here. There's no interactions. When they approach some intermediate separation, you begin to have attractions which dominate. And if you get them really close together, you can have repulsions which will actually dominate between the nuclei. And so the question is, how would this affect a PV plot? And the answer is, if molecules are attracted, right, they're going to whack the walls less hard than they would if there were no interactions. So in this region here,
Which region?
You would expect reduced pressure. And if you were in this region here, you would expect increased pressure. If molecules are repelling one another, they're going to whack the molecules even harder. And so we need some ways to handle this behavior or to describe this behavior in our gas systems. Here's how we're going to do it. I'm going to slide this over just a hair. So we're going to introduce a new variable called the compression factor Z. Z is defined in this way. Z equals PVM over RT. So you can analyze the units of this, and you will ultimately find out that Z is a unitless quantity. Right? You might be tempted to look at that and say, oh, Z equals 1. That's true for one type of gas, an ideal gas, but the pressure and volume that you put into this equation are not theoretical ideal values. They're the actual experimental ones. And so what the compression factor allows us to do is to measure the deviation of gases from ideal behavior. So here's what that same data looks like. Again, this is that CO2 data. Oops, I'm now plotting Z versus 1 over volume. If this were an ideal gas, you would expect Z equal to 1. In fact, we can see that Z is less than 1, right? If Z is less than 1, the numerator of this equation up here is less than we would expect. The pressure is lower than you would anticipate. And we would infer, right, that in this type of region, attractions dominate. On the other hand, if Z is greater than 1, we get repulsions dominate. So this is going to give us a way that we can describe non-ideal behavior. All right. Here's compression factor for a couple different gases, and you don't have to worry too much about the details, but what I want to point out to you is that different gases behave differently. So again, Z equals 1 is an ideal gas. If we have large molecules like ammonia or ethane, you can see that Z drops very quickly to something less than 1. If you have other small inert gases like hydrogen or helium, you can actually get regimes where repulsions dominate. So this behavior is dependent on pressure and the specific conditions of the measurement, but you can see that there's a variety of real gas behaviors. All right, one of the first people who theoretically described real gas behavior was Johann van der Waals. So he was working in 1873. Okay? I like pictures. So here's what Johann looked like. And Johann needed a way, that's my son, he wanted to see what Johann looked like. We need some way to describe both these repulsive forces and attractive forces that molecules can experience. And so what Johann said was that he was going to consider gas molecules as impenetrable spheres, right? So the molecules themselves are now taking up volumes, and I got to reduce the gas volume, excuse me, by the volumes the molecules themselves occupy, right? So I'm going to take V, the volume of the gas, and I'm going to modify it by this parameter B. Right? B is effectively the volume that one molecule would take up, right? This is a per molecule basis. This is on a molar basis. But this B parameter is describing the volume of molecules and is used to describe repulsive forces. With regards to the attractive forces, Johann said, I am going to imagine that the pressure is reduced by some attractive interactions between molecules. And so what he did was he took the pressure and he reduced it by some amount, which depended on how close the molecules were together. The molecules were a long ways apart. Interactions would be weak, and the pressure should approach what you would expect in an ideal type of situation. On the other hand, if the molecules are really close together and the volume is small, those attractive forces are important. And so here's his equation. Right? This B parameter up here describes the repulsive forces. We now have an A parameter, which is describing the attractive forces. Again, this is on a molecular per molecule basis. Over here is what it looks like on a per mole basis. If we put all of this together, we get up an equation known as the van der Waals equation, and here's what it looks like. So P equals RT divided by Vm minus B minus A over Vm squared. Again, this parameter here is accounting for the repulsive forces. This parameter is taking care of the attractive forces. These specific quantities A and B are tabulated values. You can find them in Atkins. So here are A parameters. Here are B parameters. And I think there's some things that you might expect. So small inert gases like helium have weak attractive forces, whereas bigger things like carbon dioxide have much bigger. You may also be surprised to find out that some noble gases like xenon It can have really strong attractive forces between them. Remember, xenon's low down on the periodic table, so it has lots of electrons. Here are these B parameters, right? And again, small molecules, small b, big molecules, big B. All right, I can use the van der Waals equation of state then to describe real gas behavior. And I'm showing you that here on this plot. Again, this is all the same data set. The solid line here is the ideal gas prediction. The dashed line is now van der Waals. And I'm just going to write that in so that you're definitely seeing it. And what you can see is that the van der Waals is a significant improvement over the ideal gas law model at predicting real gas behavior. So it's getting much closer to the experimental values, although it's not perfect. The other important thing is that when the molecules are really far apart, the van der Waals equation approaches the ideal gas law equation, and you get the same type of behavior. So this is a really important model that we can use to describe real gases. This is the same thing where I'm now plotting Z. All right, 2 last points and then we'll call it a day, or at least a video. Here's the ideal, not the ideal, this is the van der Waals equation. And one thing I've found is that students often are confused about attractive and repulsive forces. So in most chemical contexts, which is more important or more dominant, attractive or repulsive interactions? And it may or may not be clear to you, but here's the answer. Right? Attractive. Remember that in order to experience repulsive forces, the molecules have to be really, really close together, whereas to experience attractive forces, they can be further apart. So in most chemical contexts, it's the attractive forces that we're really worried about. Repulsive forces very seldomly come into play. Here's the other issue. If I were given the molar volume, I can't find my cursor, but you can see the molar volume in the van der Waals equation. I could imagine plugging and chugging and calculating P. I think that'd be relatively easy to do. But it turns out this is relatively uncommon, right? We're not often given the molar volume and asked to calculate pressure. Instead, we're given the pressure and asked to calculate the molar volume. Right? So here's the pressure. How do I calculate the molar volume? And you could start doing some algebra, see if you can solve something, but I'll save you some work and tell you that you can't. Right? There's no symbolic solution to this problem. And instead, what you'll get if you do your algebra is a cubic equation. So you'll get some polynomial, a cubic polynomial, equals 0. And as you may remember from a math or well, I guess it probably would be a math or a physics course, cubic equations we typically have to solve numerically. So the old school way of doing that is sort of plotting it on your calculator and finding where it crosses 0. If you want to solve equations that way, you can do that. You could also use more modern techniques like a solve button on a calculator or using Mathematica, NSolve. Right? If you're unfamiliar with how to do any of that stuff, please talk to me. There's some hints in Atkins about doing it, but I can probably save you a little bit of work about giving you some shortcuts and helpful ways to do that. So how would you do this? The answer is numerical solutions. All right, I will stop here and we'll see you in the next video where we talk about the virial equation, our last model for real gas behavior. How'd I do, Gus?